Welcome and congratulations for choosing this course. Be ready to learn something new and take your skills to the next level. First, I would like to outline the key components of a highly scalable and fault-tolerant microservices architecture, including the user interface, microservices implementation, and data store. I also provide guidance on building this architecture on AWS using container technologies. Additionally, I suggest AWS services that can be leveraged to implement a typical serverless microservices architecture, which can help minimize operational complexity. At the end of the course, you will have opportunity to try it out by doing hands-on lab. My name is Kevin, and I am excited to welcome you to this AWS Serverless Microservices Bootcamp. Whether you're a seasoned developer or just starting out, this series is designed to help you gain practical skills and knowledge that you can apply to your own projects. So, thank you for joining. Get ready to dive in and let's get started. In this module, we are going to deep dive into the world of microservices. Do not waste any time, let's get started. First, talk about the old way. Monolithic applications are traditionally structured into three separate layers: user interface layer, business layer, and persistence layer. In contrast, microservices architecture is based on breaking down application functionality into smaller independent units, defined by specific domains rather than technological layers. Microservices architectures are not a novel concept in software engineering. Rather, they are a combination of various successful and proven concepts that have been utilized in the past, such as agile software development, service-oriented architectures, API-first design, continuous integration, and continuous delivery. Microservices represent an approach to software development that focuses on improving deployment cycles, enhancing innovation and ownership, and scaling organizations delivering software and services. The primary objective is to enhance the maintainability and scalability of software applications by using an agile approach that helps teams work independently. This is achieved by breaking down software into small services that communicate over well-defined APIs that can be deployed independently. These services are owned by small autonomous teams, allowing for greater agility and innovation. When I talk about serverless, in AWS context, it is characterized by an operational model that adheres to these four tenets. No requirement for infrastructure to be provisioned or managed. Pay-for-value billing model. Built-in availability and fault tolerance. Automatic scaling based on the unit of consumption. This diagram is an example of a reference architecture for a typical microservices application on AWS. In AWS, there are three common patterns when building microservices: API-driven, event-driven, and data streaming. This approach is beneficial because it allows for the introduction of microservices characteristics while reducing the challenges associated with building microservices. However, the implementation of microservices requires careful consideration of specific requirements and use cases, including data store, asynchronous communication, and service discovery, in addition to the provided guidance. By using Amazon Web Services, product teams can successfully overcome these challenges and achieve greater success with their software development efforts. In this section, we will talk about the front end of a typical microservice. JavaScript frameworks are commonly used in modern web applications to enable single-page applications that can interact with a REST or RESTful API. To serve static web content, Amazon Simple Storage Service, Amazon S3, and Amazon CloudFront can be utilized. Microservices can benefit from reduced latencies by serving clients from the closest edge location and using caches or proxy servers with optimized connections to the origin. It's best to implement other caching. In this section, I will teach you everything you need to know about microservices APIs and compute. APIs serve as the entry point for applications to interact with microservices that allows access to the programmatic interfaces of a set of services, usually in the form of a RESTful Web Services API. The API processes calls from clients and can provide various functionalities like traffic management, request filtering, routing, caching, authentication, and authorization. There are various AWS building blocks available to support the development of microservices, and two popular options are leveraging AWS Lambda and Docker containers with AWS Fargate. AWS Lambda is a serverless computing platform that allows you to upload your code and leave the rest to AWS. It automatically handles scaling and availability to match your application's demand without requiring you to manage any infrastructure. You can choose from a range of supported programming languages and invoke Lambda functions from other AWS services or directly from your web or mobile app. The key benefit of AWS Lambda is its ability to accelerate development, as you can focus on writing business logic while AWS manages security and scaling. Container-based deployment is a popular approach for reducing operational efforts in deployment. Docker, a container technology, has gained popularity due to its benefits such as portability, productivity, and efficiency. However, working with containers can be complex and requires consideration of security fixes and monitoring. AWS provides two managed services: Amazon Elastic Container Service, Amazon ECS, and Amazon Elastic Kubernetes Service, Amazon EKS, to eliminate the need to install, operate, and scale your own cluster management infrastructure. Using API calls, you can easily launch and stop Docker-enabled applications, query the state of your cluster, and access familiar features such as security groups, load balancing, Amazon Elastic Block Store, Amazon EBS, volumes, and AWS Identity and Access Management (IAM) roles. Amazon ECS provides container placement strategies and constraints to enable customization of how tasks are placed and terminated. A task placement constraint is a rule that is taken into consideration during task placement. Attributes in the form of key-value pairs can be associated with container instances, and constraints can be used to place tasks based on these attributes. Docker images used in Amazon ECS and Amazon EKS can be stored in Amazon Elastic Container Registry. Amazon ECR. Amazon ECR eliminates the need to operate and scale the infrastructure required to power your container registry. Amazon EKS is a managed Kubernetes service that allows you to use existing plugins and tools from the Kubernetes community since it runs the latest versions of open-source Kubernetes software. It ensures that the applications running on Amazon EKS are fully compatible with standard Kubernetes environments, regardless of whether they are running in public clouds or on-premises data centers. IAM integration with Kubernetes enables you to register IAM entities with the native authentication system in Kubernetes, eliminating the need to manually set up credentials for authenticating with the Kubernetes control plane. This integration allows you to use IAM for directly authenticating with the control plane and granting fine granular access to the public endpoint of your Kubernetes control plane. AWS Fargate is a serverless container compute engine that integrates with Amazon ECS and Amazon EKS. It eliminates the need to provision compute resources for container applications, allowing you to easily launch and scale tens of thousands of containers without worrying about infrastructure management. Fargate is designed to support mission-critical applications with high availability and reliability. Microservices rely on the data store to retain the required data. You have multiple options for data stores on AWS. The first option is Relational Database. AWS provides 6 database engines: Microsoft SQL Server, Oracle, MySQL, MariaDB, PostgreSQL, and Amazon Aurora. Relational databases are not built for infinite scalability, which can make it challenging and time-consuming to implement techniques that can accommodate a large volume of queries. NoSQL databases prioritize scalability, performance, and availability over consistency in relational databases. A key characteristic of NoSQL databases is their flexible schema, which allows data to be distributed across partitions that can be scaled horizontally. Data is accessed via partition keys. It is important to understand that NoSQL databases have different access patterns than relational databases. Amazon DynamoDB provides impressive single-digit millisecond performance, but some use cases require even faster response times in microseconds. In such cases, DynamoDB Accelerator can help by providing caching capabilities for data retrieval. Additionally, DynamoDB features an automatic scaling mechanism that adjusts throughput capacity based on actual traffic. However, for scenarios where capacity planning is challenging or impossible due to brief spikes in activity, DynamoDB offers an on-demand option with pay-per-request pricing. This feature can handle thousands of requests per second instantly without the need for capacity planning. In this module, we will talk about reducing operational complexity. Amazon EC2 instances still require management. To further minimize the operational efforts necessary to run, maintain, and monitor microservices, a fully serverless architecture can be utilized. Let's first talk about API implementation. Designing, deploying, monitoring, continuously improving, and maintaining an API can be a demanding task that consumes a considerable amount of time. Furthermore, ensuring backward compatibility for all clients may require the operation of different API versions. This operational complexity is further compounded by the different stages of the development cycle, such as development, testing, and production. Because of this, monitoring and improving APIs is crucial for success. Amazon API Gateway is a simple solution for this purpose because it allows running APIs without server management. Authorization is a vital feature for all APIs, but developing it can be complex and repetitive. When an API is published and gains popularity, managing, monitoring, and monetizing the ecosystem of third-party developers that utilize the APIs presents the next challenge. Other essential features and challenges of API management include throttling requests to safeguard back-end services, caching API responses, managing request and response transformations, and generating API definitions and documentation with tools like Swagger. Amazon API Gateway addresses these challenges and minimizes the operational complexity of creating and maintaining RESTful APIs. With API Gateway, you can program your APIs by importing Swagger definitions using either the AWS API or the AWS Management Console. API Gateway acts as a gateway to any web application operating on Amazon EC2, Amazon ECS, AWS Lambda, or in any on-premises environment. Essentially, API Gateway allows you to run APIs without the need to manage servers. The diagram illustrates how API Gateway manages API calls and interacts with other components. Requests from mobile devices, websites, or other back-end services are routed to the nearest CloudFront point of presence, POP for short, to minimize latency and deliver the best possible user experience. In this lecture, I will show you two diagrams. The first diagram shows a serverless microservice using AWS Lambda, where the entire service is composed of managed services. This eliminates the need to design for scale and high availability, and also removes the need for operational tasks associated with running and monitoring the microservice underlying infrastructure. With Fargate, Docker containers abstract the underlying infrastructure, simplifying operations. The architecture includes Amazon Aurora Serverless, an auto-scaling configuration for Amazon Aurora. It allows for automatic startup, shutdown, and capacity scaling of the database based on the needs of the application. In combination with DynamoDB, these services provide a highly scalable and manageable infrastructure. To store persistent data, a stateful backing service such as a database is required. In a microservices architecture, disaster recovery efforts should focus on downstream services that maintain application state, such as file systems, databases, or queues. When creating a disaster recovery plan, these services should be given priority. The recovery time objective, RTO for short, refers to the longest permissible time gap between the service outage and its restoration. This objective establishes a time window that is deemed acceptable for service unavailability and is defined by the organization. The recovery point objective refers to the maximum acceptable time period between the last data recovery point and the service interruption. This objective defines the acceptable level of data loss and is established by the organization. This section examines high availability options for different compute services in AWS and options for deploying Lambda-based applications. Amazon ECS simplifies running containers in a highly available manner across multiple availability zones within an AWS region. Amazon ECS includes multiple scheduling strategies that place containers across clusters based on resource needs and availability requirements. Amazon ECR hosts container images in a highly available and high-performance architecture, which enables reliable deployment of containerized applications across availability zones. Amazon ECR integrates with Amazon EKS, Amazon ECS, and AWS Lambda to simplify the development to production workflow. Amazon EKS, Kubernetes control and data plane instances are distributed across multiple availability zones for high availability. Amazon EKS automatically replaces unhealthy control plane instances and provides automated version upgrades and patching. The control plane is deployed across at least 2 API server nodes and 3 ET nodes in 3 different availability zones within a region. AWS Lambda runs functions in multiple availability zones to ensure availability in case of a service interruption in a single zone. If you configure your function to connect to a VPC, specify subnets in multiple availability zones for high availability. AWS CloudFormation is a service that automates the process of setting up your AWS resources, freeing up more time for application development. Simply create a template that outlines the desired resources, and CloudFormation takes care of the rest, including provisioning and configuration. The service eliminates the need for manual configuration and management of resources, and ensures that dependencies are resolved. Here are some examples of how CloudFormation can be beneficial. The AWS Serverless Application Model simplifies the process of defining serverless applications. It's natively supported by AWS CloudFormation and uses a straightforward syntax to express serverless resources. To deploy your application, create a CloudFormation template that includes the required resources and permissions policies, package the deployment artifacts, and deploy the template. AWS SAM also includes SAM Local, a CLI tool that enables you to develop, test, and analyze your serverless applications locally before uploading them to the Lambda runtime. SAM Local creates a simulated AWS runtime environment for local testing purposes. A Lambda function serves as the backend of your API, ensuring that your code runs only when necessary and automatically scales to handle varying volumes of traffic, ranging from a few requests each day to thousands per second. So now we are going to use a Lambda for the simple backend. To create a Lambda function, first we need to sign into the AWS console. By the way, everything that we do now is within the free tier. First, we need to go to the Lambda console. Here you can create and manage Lambda functions. Click Create Function. For the function name, you can write what you want. I stick with my function. The runtime should be Node by default, and it's fine. Same for architecture. And note that Lambda will create a role for itself. Now click Create Function. The function is created, and here you can see the sample code. It returns hello from Lambda. Next, we need to create an API gateway. Go to the API Gateway console. To create the first API, press Build. Press Add Integration to add integrations, and because we use Lambda, press Lambda. Choose your region and your function, so I press my function. Give it a name, for example API or something, and press Next. 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 And create. To test our API with Lambda integration, first copy the invoke URL. Insert it into your browser, and append your function name after it. As you can see, we get the hello from Lambda message back. If you go back and edit the message from hello to hi, deploy it, and test it again, and as you can see, you get that back. We are ready with our mini project. With this type of architecture, you can build a whole backend for your microservice. Now I just wanted to show you how easy it is to get this started. I really encourage you to try things out and build this project further on your own, But if you are done or in the future you want to delete everything we created, follow along with me. First, go to the API console. Select the gateway that you created, go to Actions and select Delete and press Delete. After that, go to your Lambda functions, select it, go to Deletion, same way again, type Delete and again press Delete. Press Close. To really delete everything, we need to go to the CloudWatch console. Press Logs and select Log Groups. Here select and go to Actions and delete it. After this, we have one last step. Go to IAM console. Go to Roles and search for your function name. Delete the roles that your function created. That was the hand-on lab where we created and tested an API gateway integrated with Lambda function. I hope everything was clear and you enjoyed it.